Hello everyone, and welcome to the Toy Car Pre-Lab. So check out this little, what we call a toy car. Actually, this really expensive little high-tech physics car that we're going to use in several labs this year, and just kind of watch its motion. And so watch that motion again, and what do you notice about that motion? Well, some of you might be noticing that it seems to be going in what we might call a straight line. As much as we can make these things do that. We even have little tracks sometimes that they'll ride on to keep them in a nice straight line. Well, in physics, we tend to call things moving in straight lines one-dimensional motion. Right? So in this unit, we are going to be looking at one-dimensional motion. We do look eventually at a couple of special cases of two-dimensional motion, and we save 3 dimensions until you get to AP Physics C. So right now, one-dimensional motion. But again, watch the motion. I think there's something else going on here. Most of the times, some people will say, well, something about it seems constant about that motion. Well, what seems constant? Here's where we're gonna run into a bit of an issue when doing this pre-lab in class, which is that I'm not going to let you use physics words unless you can properly define them. These might be words that you use in common English, right, but you actually don't have a really good definition of what they are. I mean, for example, think pi, right, that we came up with in a couple of the different circle labs. You've got a much better understanding of where pi comes from and where it exists in nature than you did perhaps before doing those labs, right? So this is kind of like that. So if you're using words like speed or velocity or the math rate, right, to try to describe this motion, I'm not sure that you can actually define that appropriately, at least in physics terms. So can we break this down? What seems constant about this motion? My supposition here is that there seems to be something constant about the distance it's moving in a certain amount of time. Now, certainly, I hope we all can understand what distance means, right? How far it goes, and time, right? In seconds, say, or something like that. So let's do a lab in this case where we break this motion down into, as basic of a thing as we can, distance and time. So the purpose of this lab, as you will see at the top of your lab sheet, is to create graphical and mathematical representations of the relationship between the distance and the time of your toy car. Okay? So, 2 variables, right? One has to be the independent and one the dependent variable. Well, we actually could do this lab either way. We could do this lab where the distance is the independent variable, the one we control, and the time is what we then measure, the dependent variable. For example, we could choose some distances. We could let the car go 20 centimeters and measure how long it took. We could then let the car go 30 centimeters and measure how long it took. Right? That would be controlling the distance and measuring the time. However, because I want the graph to be organized a certain way, because I want the slope of that graph to be rich in meaning, as we're going to see, we are going to do the lab the opposite way. We are going to have our time as our independent variable and our distance as our dependent variable. Right, so we are going to choose a time to let the car run and measure the distance it covers. Then choose a different time, measure the distance it covers, and so on. So when it comes time to making a graph, which variable goes on the vertical and which variable goes on the independent? That's right, independent variable, on the horizontal axis, dependent variable on the vertical axis. We'll be making graphs of distance versus time. Distance in centimeters, time in seconds. Okay, will be the graphs that we will make out of this, and then we will get meaning from that and build math models and all that good stuff. Now, there is one issue with running these toy cars, which is that, as you will see, they run on batteries. And so if we're running trial after trial after trial after trial in the class, what might happen? Think of the little electronic cars you maybe have played with over your life. Well, eventually, of course, the batteries might start to run down. And if the batteries start to run down, that might affect the motion of the toy car, and that's a variable we don't want to have to deal with. Right? So we want to kind of hold the batteries constant. To do that, I'm going to show you a way to run this lab so that you can get all of your data in a trial instead of running a 3-second trial, a 6-second trial, a 9-second trial, and so on. Okay? So this is what we're going to do. You are going to, or someone in your group is going to download a metronome app. If you're in band or choir, you may already have one on your phone, and that would be fine. A metronome, if you remember, is a device that used to sit like on your piano, and you'd pull it to the side, it would go back and forth and click every time it went from side to side, and you could change it so that it would go at a different rate, right? So that it would click at different beats per minute. Okay, so I want you to find a metronome app. You're going to set your metronome app so that it makes a click, a noise, every 3 seconds. Right? Every 3 seconds means it's going to make 20 beats per minute, 20 BPM if your app works in that way. All right, so you're going to set it at 20. It's going to make 20 beats every minute, which is 1 every 3 seconds. Now, please don't spend any money on this. You should be able to get a free metronome app. I have one on my phone that's old that actually looks like a metronome, that you can actually touch the little arm to it, pull it to the side, and let it go, right? And it goes kind of side to side and clicks. You don't need one with lots of bells and whistles unless you want to play with it. Right? Again, if you already have one, it should work. So set it to 20 BPM, 20 beats per minute, or 1 beat every 3 seconds. Then you're going to pick up some little blocks, okay, from the back of the room, and your toy car, and a measuring tape. You're going to start out somewhere on the floor. Please don't run these on the tables because I don't want them falling off the tables. Again, they are expensive. So you'll find some room on the floor you can work, somewhere in the room where you're away from everybody else. You'll let the cart go, and then you'll start your metronome app, let the cart go, and then every time it clicks, you're going to put a block down on the floor. So again, start the metronome app, let the car go. Every time it clicks, you put a block down. You do not have to synchronize when you let the car go and when you start the metronome app or anything like that. Okay, the car can run, and then when it clicks, you put the block down. Okay, it's going to look something like this. And so on. Now you actually have 6 blocks to put on, right? But that's the way this will look. Okay, when you're done on the floor, you'll see your blocks out on the floor. Then you're going to take your measuring tape and measure things. Well, notice the first block you put down is what we're going to call 0 centimeters. That's where you'll put the end of your measuring tape, and 0 seconds. So we're actually going to have a 0 point in our data table. Okay? Again, you don't have to sync this with when you start the cart. You can let the cart go, and then you can put the block down when you hear the click. Okay? You might have to follow that person who's, placing the blocks with your phone so that they can hear the clicks, because there's going to be a bunch of groups working at the same time, but this can be done. Okay? Use your measuring tape. That would be your 3-second distance. Then this would be your 6-second distance. And that would be your 9-second distance, and so on. Note, we are not measuring the intervals between the blocks. We are measuring from 0 to there. So this is as if we ran a single trial and let it run for 3 seconds. This is if we ran a trial and let it run for 6, 9, right? But instead of running trial after trial after trial, we're running them all at once. I know, clever, isn't it? Right? And you'll have a 12-second and a 15-second trial as well out there. I know these look like Legos. That's what I used to use, right? But we have some little blocks now from Mr. Kawa that we use, but Legos work just as well. So you'll have this little pattern. You're going to measure it, and of course we're going to put it into a data table. Time in seconds. Distance, please measure in centimeters, and yes, estimate using the measuring tape. That's proper sig figs. Note that I would like you to run this 3 times and take an average. Okay? Average goes here. When you graph, you only graph the average distance. I don't want the 3 trials, right? The 3 trials are to try to help us mitigate some error, okay, by taking an average. Your 3 trials should be pretty close to one another. If they're wildly different, something happened, and you're going to want to redo a trial and throw out the bad one, okay? It's not hard to redo these, right? It only takes like 15 seconds to run a trial. So, get 3 good ones. If you think somebody put the block down wrong, get rid of it. If they didn't hear the metronome on your phone, get rid of it, do a new one. Physics is nice that way. We can tend to repeat ourselves and take averages. By the way, sometimes people will ask, well, where do we put the block? Do we put it at the front of the car, the middle of the car, the back of the car? And my answer to you is, does it really matter? Really doesn't. Just be consistent. Don't put the first block down at the front of the car and the third block down at the back of the car. Right? Otherwise, you've cut the width of the car off. Right? So, use the front of the car or the front wheel or the back of the car and the back wheel, whatever you want to use. Just be consistent with it and everything should work out well. So because of the way that we are calling our first block 0 time and 0 centimeters, this is actually a data point that you can put into your data table and that you will put into your graph. Okay, so we actually have a true 0, 0 in this lab. And then you're going to put your other data in here. Now, one key thing about these carts. You're going to see on the top of them that there is a knob. And that knob is called speed. It says speed right around it. We don't know what that means yet. So don't play with the speed knob. Right? Do not turn the speed dial on the car. If you change the speed dial, you have just changed another variable in your lab, and all your previous data no longer matches your new data. And you have to start all over again. They are set to kind of run somewhat slowly, which is fine. Don't worry, you will get a chance to play with the speed knob in our next activity, just not in this one. So please don't play with the speed knob. Okay? If somebody in another hour has cranked it all the way up, you might need to call me over to change it because, we don't want you running into the wall across the room before you get your last block put down, right? But hopefully it's set at a nice moderate speed. After you're done, you make your graph, you linearize, you do your line of best fit, you then can finish the rest of your lab sheet. And then we will do a post-lab in our next class where we will discuss what we're learning about the motion of this toy car.